So this video is going to be looking at these covalently bonded molecules and how do they demonstrate themselves in 3 dimensions. So what is their 3-dimensional structure of these molecules, So it stands for VSEPR theory, valence shell electron pair repulsion. So valence shell electron pair repulsion. What you need to know is valence electrons determine the shape of the molecules. And so these outermost at the highest energy level electrons are going to determine how do the bonds themselves orient themselves. So the structure is based on these pairs repelling because again, they're all negatives. So they're going to not want to be by anybody else. And so they're going to try to get as far apart as possible. Okay, so it's going to spread them out as much as possible. So for these different shapes, I'm going to give you a formula, a structure, and then the shape associated with it. So the first one I'm going to draw is the one that is kind of the basis for a lot of shapes, and that is called a tetrahedral. So for each one of these shapes, I'm going to draw the structure. And so this is CH4, this is methane, So methane, you're going to have carbon in the middle, and you're going to draw 4 hydrogens attached to it with single bonds. Well, the issue you have when you are drawing it on a flat piece of paper is this angle here between the hydrogen and the hydrogen looks like it's 90 degrees. But in reality, that's a 2-dimensional drawing, okay? So what does this look like in 3 dimensions? Well, it spreads itself out into what we call a tetrahedral, so that it spreads it out to a bond angle of about 109.5 degrees. And that is indicative of a 4-bonded central atom. So when I do these shapes, I'm going to always focus on the central atom in terms of what is bonded to it. It doesn't matter what is attached to the element, the central atom. What matters is that central atom and how many bonds it has around it. So the central atom, if it has 4 bonds in 0 lone pairs, we are going to call this a tetrahedral. So 4 bonds and 0 lone pairs, that's going to be what we call a tetrahedral shape. Next one is going to be NH3. So write down NH3. This is called a trigonal pyramidal. So I'm going to draw nitrogen in the middle and 3 hydrogens attached. But again, nitrogen is going to have a lone pair on itself. Otherwise, it will not complete its octet. So sometimes you're going to see this little balloon drawn to show that I have a lone pair on that central atom. So trigonal pyramidal, it starts off as a tetrahedral, and you essentially take one of the bonds away and replaces it with a lone pair. So this bond angle is a little different because the lone pair doesn't like the bonds themselves. So instead of being 109, it's around 107. So it's slightly smaller. But what you need to pay attention to is that central atom again of nitrogen has 3 bonds and 1 lone pair. Okay, 1 lone pair. 1 lone pair and 3 bonds is always going to be a trigonal pyramidal, All right, then a very famous molecule of water. Okay, now hydrogen, 2 hydrogens, and an oxygen. So when you are drawing this, it doesn't have to be drawn this way, but I draw it this way because I know that that's how it is in 3 dimensions. So I have 2 lone pairs on the oxygen because oxygen has 6 valence electrons. And so then you have the 2 hydrogens attached. So these lone pairs, again, this is kind of the backbone is a tetrahedral, but what you're seeing is just the bonds. So the distance between these 2 bonds is about 104.5 or about 105 is going to be sufficient enough for our discussions. And it kind of looks like a little face there. If you think of these are the eyes and the eyes are closed, and this is like a smile or something. So this is what we call a bench shape. So if I look at my central atom of oxygen, okay, I have 2 bonds and 2 lone pairs. So 2 bonds and 2 lone pairs are going to be what we call a bench shape, because when we're looking at all of these shapes, we're only looking at the bonds themselves. We're not looking at the lone pairs. So the lone pairs are essentially invisible to us. All we could see is the hydrogens. So if I draw oxygen with the 2 hydrogens without the lone pairs, that's going to be what you essentially see as the shape. That's what you see as the shape. All right, so 2 other ones. One is linear, and linears are hard to find. They're not as common as some of the other ones. So I'm going to draw you CO2 because it is a interesting molecule when you actually count up its valence electrons. So carbon has 4 valence electrons, oxygen has 6, but there are 2 of them. So you should have 16 total. So you should have 8 lines in the structure. You have 8 lines in the structure. So I'm going to put carbon in the middle and then oxygen to either end. So I'm going to try to put some lone pairs on everybody to kind of make them satisfy their octet, but then carbon isn't satisfied. So I actually need 2 other lone pairs on carbon. Well, when I count up the lines, this is 4, this is 8, and then I have 10 lines. So that's too many lines. I can only have 8 lines. So whenever you're drawing these molecules, if single bonds don't work, try a double bond. If 1 double bond doesn't work, try 2 double bonds. So in this case, 2 double bonds actually are necessary in order for you to complete the octet and to have 8 lines around it. So each oxygen has a lone pair on it, 2 lone pairs, and the carbon in the middle has 2 double bonds. Well, when you force that to happen, you're going to make what we call a 180-degree angle there between those 2 bonds. So this is what we call a linear shape. Not a typical linear shape, but we're going to say if the central atom has essentially 2 bonds around it and 0 lone pairs, that's going to be considered a linear shape with a bond angle of 180. So you might be saying, well, that's not 2 bonds, that's actually 4 bonds. But in reality, there is what we call 2 locations. So this is a location for 4 electrons to make a double bond. This is another location. So you really just have 2 places outside that carbon that you have bonds. So 2 bonds doesn't necessarily mean only single bonds. You just have 2 locations where the bonds can be. And the last shape that we're going to talk about, but again, there are other shapes out there, is called trigonal planar. Trigonal planar. Now this one is actually in 2 dimensions, is actually drawn the same way as 3 dimensions. So boron is one of those weird exceptions that it only makes 3 bonds. It does not complete its octet. So I'm going to put boron in the middle, and then I'm going to put 3 fluorines around it. And the furthest I could get 3 bonds is 120. So if you think of a circle at 360, 360 divided by 3 is going to give me a bond angle of 120. So I can't forget my lone pairs on fluorine. And again, just because fluorine has lone pairs doesn't mean those are the lone pairs we're talking about. We are only focusing on the central atom when we're talking about the 3 dimensions. So again, write this down as 2 dimensions is the same as 3 dimensions. So it is flat, it is a triangle. So trigonal planar means it's in the same plane, and it is a triangle. So what exactly is the central atom seeing? It is seeing 3 bonds and 0 lone pairs. Okay, so 3 bonds and 0 lone pairs. That's going to be a trigonal planar, trigonal planar. So we have given you a list of these shapes, okay? And these shapes, again, got this from some book many years ago, have, again, a certain way of drawing them. So just a couple things to mention about the chart. So total pairs of electrons is in this column here. Shared pairs is going to be, again, the bonds. Okay, what kind of bonds do you have around that central atom? And lone pairs is exactly what it sounds like. That's the lone pairs. But again, this is only the central atom is all we are talking about here. So it has nothing to do with the lone pairs that are, say, for instance, the one I just drew. It doesn't matter that I have 3, 6, 9 lone pairs on fluorine to get total. What I care about is what is the lone pair on that central atom. So again, just like I went over, linear is going to be 2 and 0. Trigonal planar is going to be 3 bonds and no lone pairs. Tetrahedral, 4 bonds and no lone pairs. So on this diagram, you will also see these little balloons. Okay, so that is where the lone pairs are. So I have 2 lone pairs on the bench shape. I have 1 lone pair on the trigonal pyramidals. We sometimes see books put that because the electrons still take up a space. Okay, they take up space, and that's why they have the shape that they do. But it's not a bond. It is not a bond. And please realize with these bond angles, for all intents and purposes, this is close to 109. This is close to 107. This is close to 105. So every time you add a lone pair, you're going to subtract 2. So you're going to go from 109 to 107, and then 107 to about 105 is going to be the bond angle there.